Assalamualaikum and hi, my name is Hakim Bmkc and today I want to share you how I get answer for question 1a. To find the half range Fourier cosine series, I begin by identifying the series structure for a range of 1 where the sine terms are set to 0. I started by calculating the constant term by integrating the function 3 exponent power of 2x from 0 to 1. After evaluating that integral, I arrived at a final value of 19.167. Next, I move on to calculating the coefficient for the series by integrating the function multiplied by the cosine terms over the same range. To solve this, I use the tabular method to organize the repeated derivatives and integrals, which allowed me to determine the resulting expression. After substituting the boundaries of 0 and 1 into expression, I simplified the result to the form shown here, which is equal to 12 exponent power of 2 times negative 1 power of n minus 12 over 4 plus n squared pi squared. Finally, I assembled the complete series. I took the constant 19.167 and divided it by 2 to get 9.584, which serves as the leading term. I then added this to the summation of the coefficient I just derived to produce the final expression for the cosine series. Thank you.
Assalamualaikum, my name is Muhammad Ifan Adam bin Muhammad Akmazani. My matrix number is B112510126. Okay, first of all, we start with the standard general form for a half range Fourier cosine series. Here we have a constant terms A0 over 2, which represent average value of the function. Then we have a an infinite sum over the integer n of an amplitude coefficient an multiplied by a cosine terms. Since we are only looking for the first three terms, we are focus on n equal 1, 2 and 3. Next, we evaluate the specific coefficient for this problem. Our calculate constant terms A0 over 2 comes out to be approximately 19.17 divided by 2. For the an coefficient, we have a general formula 12 times the quantity e squared times negative 1 to the power of n minus 1. This is divided by the denominator for plus n squared times pi squared. On the screen, you can see I have written out this formula. First three terms n equal 1, n equal 2 and n equal 3. Step 3. Now performing the arithmetic, we arrive at our final approximation. The constant term simplifies to 9.58. For the first non-zero terms, when n equal to 1, the coefficient evaluate to approximately negative 7.2582, giving us the terms negative 7.2582 over cos over pi x. For the second terms, when n equal to 2, we get plus 1.76 times over cos 2 over pi x. And finally, for the third terms, when n equal to 3, the coefficient is negative 1.08 times over cos 3 over pi x. The conclusion is this equation represent our final using Fourier cosine approximation, using only the first three non-zero terms.
Assalamualaikum, my name is Amirun Jester. Number matrix B1125159. Moving on part C, let's look at why the cosine series is suitable for insulated boundaries condition in heat transfer problems. Okay, to understand this, we need to look at the two main points. First, physically, an insulated boundaries means there is zero heat flux, which require the temperature gradient to be zero at the boundaries. Okay. For the second point, mathematically, the derivative of a cosine function is a sine function. Since sine naturally equals 0 at the boundaries, the cosine series inherently satisfies the zero gradient condition.
And
Thank
good
you.
day everyone. My name is Muhammad Abdul Hakim bin Azman. So for question 1D, we are asked to find the half range Fourier sine series for the function tx equal to 3 exponent to x over the interval from x equal to 0 to 1. So the formula for tx is sum from n to infinity bn sine n pi t over L. Because it is a half range sine series, so our L is equal to 1 and a naught and an are equal to 0. So we only need to find bn, which the formula for bn is bn equal to 2 over L integral from 0 to L ft sine n pi t over L dt. Since L equal to 1, we will get bn equal to 6 integral from 0 to 1 exponent 2x sine n pi x dx. To solve this integral, I use the tabular method, which is a faster form of integration by parts. I differentiate the sine function and integrate the exponential function repeatedly. And if we apply the integration by part twice, the original integral reappears on the right side. So by moving it over and factoring it, we isolate the indefinite integral. So I obtain the result 6 integral exponent to x sin n pi x equal to 6 in bracket exponent to x in bracket 2 sin n pi x minus n pi cos n pi x over 4 plus n square pi square with the limit 0 to 1. Then I substitute the limit from 0 to 1. So using the sin n pi equal to 0, cos n pi equal to negative 1 power of n, sin 0 equal to 0, cos 0 equal to 1. I obtain bn equal to 6 exponent square in bracket minus n pi in bracket minus 1 n minus negative 1 over 4 plus n square pi square. Then I factor out the 6 n pi. I will get 6 n pi in bracket 1 minus exponent 2 in bracket negative 1 power of n over 4 plus n square pi square. Finally, we substitute bn back into our general Fourier series summation. So tx equal to the infinite sum from n to infinity of 6n pi in bracket 1 minus exponent 2 negative 1 power of n over 4 plus n square pi square multiplied by sine n pi x.
So the question is explain when the sine series is more appropriate in mechanical system. The first is in many mechanical systems such as vibrating strings, simply supported pin-to-pin beams, and fixed rods. The natural standing wave patterns are represented by the sine function. This system often have fixed boundaries that require the displacement of force at the end to remain zero throughout the motions. And since the sine function equals to 0 at both x equals to 0x and x equals to n pi x, each sine term automatically satisfies these boundary conditions, eliminating the needs for additional modifications.
In this part of the solution, we are setting up the physical constraints for our problems. First, let's define the boundary condition that will apply for all times t greater than 0. We can see that our system is fixed at both ends. At position x equal to 0, the function u is equal to 0. Similarly, at position x equal to 30, the function is also equal to 0. This fits and represent our boundary condition. Step 2. Next, we need to determine the initial shape of our function at time t equal to 0, which is denoted as u x 0. The problem defines this over two different regions from x equal to 0 to 10 and from x equal to 10 to 30. Let's calculate the equation for each segment. Step 3. For the first segment between 0 and 10, we pass through the origin at point 0, 0 and end at the peak of point 10, 3 because this is straight line. We can use the slope-intercept form y equal to mx plus c. We calculate the slope m by taking the change in y over the change in x, that is 3 minus 0 over 10 minus 0, which give us a slope of 3 over 10. So for this range, the equation is simplified 3 over 10 times x. Step 4. Now for the second part, from x equal to 10 to x equal to 30, this line start at the peak 10, 3 and drop down to 30, 0. Again, we calculate the slope. This time, the rise is 0 minus 3 and the run is 30 minus 10, resulting in a slope of negative 3 over 20. To get the equation, they use the point slope form is written as usual u x 0 equal to negative 3 over 20 times x minus 30. If we expand that or simplify it visually, it is mathematically equivalent to 30 over 20 times 30 minus x, which show the head decrease as x increase. Step 5. If x is between 0 and 10, the initial condition is 3 over 10x. If x is between 10 and 30, the initial condition is 9 over 2 minus 3 over 20x.
So next for question 2b, we are given the one-dimensional wave equation utt equal to 9uxx, and we need to determine the solution uxt using the method of separation of variable. So the first step is to assume that the solution can be written as uxt equal to xx dt. So then we substitute the uxt equal to xx dt into the wave equation and divide by xt. We will obtain t double prime over 90 equal to x double prime over x equal to p. So we will get t double prime minus 9pt equal to 0 and x double prime minus px equal to 0. After that, we will do the boundary condition. So the boundary condition are u in bracket 0 t equal to 0 and u in bracket 30 t equal to 0. Since uxt equal to xx dt and tt cannot be 0, so the boundary condition becomes x0 equal to 0 and x30 equal to 0. For next, we will examine the possible case, which for case 1, we let p equal to 0. So the equation become x double prime equal to 0, and we will use the solution xx equal to a plus bx. So we apply the boundary condition x0 equal to 0, we will get a equal to 0. We apply x30 equal to 0, we will get b equal to 0. So we will get xx equal to 0, so we will omit the solution. And next we will consider case 2 where p more than 0. So we let p equal to lambda square. The equation becomes x double prime minus lambda square x equal to 0. And the solution is xx equal to a exponent lambda x plus b exponent negative lambda x. We apply the same boundary condition again, and we will get a equal to 0 and b also equal to 0, which we will also omit the solution.
Now for the case 3, to solve our differential equation using the separation of variable methods, we begin by analyzing the case where our separation constant p is negative, we can define p as negative lambda to the power of 2. Substitute this into our spatial equation gives us x double prime plus lambda to the power of 2x equals to 0. To solve this second order linear differential equation, we write out its characteristic equation, which is m to the power of 2 plus lambda to the power of 2 equals to 0, which yields the imaginary roots of m equals to plus minus I lambda. And because the roots are purely imaginary, the general solution for our spatial function takes a trigonometry form, which is x parenthesis x equals to a cos parenthesis lambda x plus b sine parenthesis lambda x. Now, we apply our first boundary condition, which states that x parenthesis 0 equals to 0 since cos parenthesis 0 equals to 1 and sin parenthesis 0 equals to 0. This forces our constant a to equal to 0. With a equals to 0, our spatial equation simplifies to x parenthesis x equals to b sine lambda x. Next, we apply our second boundary condition at the other boundaries, which is x parenthesis 30 equals to 0. This gives us the equation b sine parenthesis 30 lambda equals to 0. To avoid a trivial solution where everything equals to 0, we can see the b cannot be 0. Therefore, sin parenthesis 30 lambda must equal 0. This implies that the angle 30 lambda must be integer multiplier of pi or n pi. Solving for lambda, we get our inch values of lambda equals to n pi over 30. So the final spatial solution is plugging our eigenvalue back in, we obtain our final spatial eigenfunction, which is xn parenthesis x equals to b sine sin parenthesis n pi x over 30. So now we move on to the time dependent for our separation of variables. Our equation for time is given by t double prime over t equals to 9p. Substitute our knowing value of p equals to negative lambda to the power of 2. We rewrite this as t prime double prime equals to negative 9 lambda to the power of 2t, which simplifies to the standard form, which is t double prime plus 9 lambda to the power of 2 t equals to 0. Just like before, we look at the characteristic equation, which is m to the power of 2 plus to 9 lambda to the power of 2 equals to 0. Solving for m gives us the imaginary roots of m equals plus minus 3 lambda. Note that the square root of 9 outputs a factor of 3 in front of our frequency terms. This leads to the general time dependent solution, which is t parenthesis t equals to c cos parenthesis 3 lambda t plus d sine parenthesis 3 lambda t. Okay. Next, we substitute the eigenvalues we found earlier, which is the lambda equals to n pi over 30 into the equation. The 3 and the 30 simplifies beautifully, leaving us with our final time function, which is t parenthesis t equals to c cos parenthesis n pi t over 10 plus d sine n pi t over 10. Now, since our total solutions u parenthesis x and t is product of x parenthesis x and t parenthesis t, we multiply our two results together to get the function and to get the fundamental product solution shown here on the slide. So by applying the principle of superposition, we can express the total general solution as an infinite series sum of all possible solutions. Combine our new Fourier coefficient an and bn. Finally, we apply our initial condition at t equals to 0 because the initial velocity or condition forced the sine term to vanish, specifically because sine 0 equals to 0. The coefficient Bn becomes 0. With Bn equals 0, our equation simplifies down completely, gives us our final solution for this wave profile over time, expressed as clean cosine Fourier series.
For this part, to determine the coefficient for this series, I begin by splitting the integral into two distinct segments, covering the intervals from 0 to 10 and from 10 to 30. I set up the full expression for an as the sum of these two integrals, incorporating the specific functions for each range. To solve this, I utilize the tabular method to systematically organize the repeated differentiation and integration for both parts of the functions. By carefully following this method, I generated the corresponding term, which I then compiled into the large bracket expression shown here. From there, I performed the boundary evaluation at 0, 10, and 30. During this stage, I simplified the expression by cancelling out several terms, particularly where the sine and cosine evaluations at the boundaries reduced to 0 or common values. Moving to the final solution steps, I grouped the remaining terms and carefully distributed the values to isolate the variables. This algebraic process allowed me to condense the long expression significantly until I reached the final simplified form for the coefficient, which is equal to 27 divided by n times pi squared multiplied by the sine n times pi divided by 3. With this coefficient determined, I concluded by substituting it back into the general series summation formula for uxt. This gives the complete series representation where the term I just calculated is multiplied by the cosine of n by t over 10 to form the final solution. Thank you.
Okay, moving on to part 2c, we are tasked with calculating the specific value of the function uxt when the position x is 50 cm and the time t is 5 seconds. Okay, if you look at the top of the answer of question 2c, the first thing we do is substitute these values directly into our main equation by replacing t with 5 and x with 15. The fractions simplify really nicely. The cosine term simplifies to cos and pi over 2, and the sine term at the back also becomes sin and pi over 2. To see what happened to this summation series, we can test it by expanding it for the first few value of n. Okay, starting with n equals to 1, the middle terms cos pi over 2. Since cos 90 degree is 0, it completely wipes out the entire term, giving us a result of 0. Okay, for the next, for n equals to 2, this time the cosine term doesn't equal to 0, but the last term sin pi, because sin 180 degree is 0, it again causes the whole expression for n equals to 2 to drop out to 0. Okay, for the last one, n equals to 3, the pattern repeats. The middle term becomes cos 3 pi over 2, which is 0, making this term vanish as well. Okay, as we can see, due to the alternating behavior of the cosine and sine function, at least one of these components will always hit 0 for every single integer value of n. Because every single term in the infinite series equals 0, the entire summation collapses. Therefore, we can confidently conclude that our final answer is U50 equals to 0 cm. Okay, thank you.